Hello there. I recently found myself wondering how effective large language models are at reverse engineering. To put them to the test, I decided to take on the well-established annual challenge by Mandiant, known as Flare-on 11. Stick around to see how it went. The first challenge is called Frog. I used Cursor's default agent chat window and typed,
How do I win this game? The walls seem solid. Take a look at frog.py.
followed by the task description and a picture of the game. It nailed it right away.
Most blocks are created with passable equals false, but there are two special blocks created with passable equals true.
And it provided their addresses. Wow, an instant solution without even reading the source code, let alone running a modified version. Not bad at all. The next challenge is a binary file with no explanation provided. When you run it, it first presents a simple math problem to solve, and then it asks for a checksum, hinting that you should inspect the binary itself. When you open the binary in IDA, a few things stand out right away. First, it's written in Go, which doesn't use the fast call calling convention, so the default decompilation output won't be very helpful. Second, the main entry point appears to be a function named main.main, and it's relatively readable in the assembly view. The good news is that the symbols are intact. Let's move on to the next step, exporting the full assembly of the file into an .asm file. Go to File, Produce File, Create ASM file. Once that's done, we'll copy the main function and paste it into the LLM to get an explanation. I chose the Gemini 2.5 XB model because Cursor's default one wasn't working that well. You can pause the video and read the full explanation yourself. I'll just point out the key parts.
It expects the input string to be a hex-encoded string. It decodes this hex string into a byte slice. It expects the resulting byte slice to be exactly 32 bytes long. It uses the 32-byte key derived from the user's input to decrypt an embedded data block.
So far, so good. However, there is something interesting happening after the decryption.
It calculates the SHA-256 hash of the decrypted data. If the calculated hash matches the user's input checksum string, it calls another function, main A. Regardless of the match, it takes the decrypted data, constructs a file path, and writes the decrypted data to that file.
Something strange is going on in the main function. Let's copy its disassembly into the context and take a closer look. Stop the video to read full answer. I'll just summarize here.
This function is essentially verifying if the input data correctly decodes to this target base 64 string when XO read with Flare-on 2024.
Aha. So the decrypted data is hashed again and compared to an obscure value. Remember, the input was also a hash. Maybe they're the same. Let's see if the LLM can reverse the check performed by the main A function. I created a new .py file and placed the base 64 encoded string inside it, since it wasn't visible in the assembly accessible to the LLM. Then I asked it to complete the script, and magically it worked. The script produced a value that passed the checksum challenge. The flag is an image file written in app-data local directory. Challenge number 3 is about Yara rule matching. You're given around 500 rules for an 85-byte file, and the goal is to satisfy all of them to get the flag. If you add a new line after each AND keyword, the rules become much easier to read. There are roughly 3 types of checks: 2-byte hashes, strong 4-byte comparisons, and weaker 1-byte comparisons. The first two provide the most insight, while the third type likely requires Z3 to solve. If you're unfamiliar, Z3 is a theorem prover that's widely used for solving problems like this. You can think of it as an intelligent brute forcer. I tried several LLMs in Cursor, but they struggled with a few things. First, they didn't recognize that the 2-byte hash and CRC checks could be brute forced easily. Second, they didn't default to using Z3. Even after giving hints about brute forcing in Z3, they still couldn't put together a working solution. I was about to start coding it myself, but gave Gemini a try via the web interface. Surprisingly, Gemini solved the challenge on the first try. You can pause to read the full prompt, and the code is available in the attached GitHub repository. Pretty cool. Didn't have to write a single line of code to get the flag. Also, Gemini noticed a few contradictory rules and commented them out. I'm not sure if that was a false positive or intentional, but I didn't bother checking since I already had the flag. The fourth challenge is called Meme Maker 3000. It's a single HTML file that embeds both data and JavaScript. When opened, it lets you choose from various meme images and add your own text. The first thing you'll notice is a script tag in the HTML, which is slightly obfuscated. The script is quite large due to several data variables that hold images and other content. I replaced these with triple dots to make the code manageable for an LLM, otherwise it would exceed the context window. So I asked,
Analyze what is this code doing? I'm looking for hidden flags. Keep in mind there was much more data in elements which contain triple dots.
It essentially explained how to get the flag.
This is where the flag logic resides. It checks for a specific combination of meme template and caption text.
It also tried to generate the flag on its own, but it was obviously incorrect. So I followed up with,
Produce me a JavaScript snippet which I'll paste into browser's console when this specific page is loaded, and that script should force existing code to show the flag.
I received a 4-line snippet, but it didn't work as is. Running it line by line, I noticed one of the variables wasn't updating correctly. Manually copying and pasting the string directly did the trick. It triggered the dialog containing the flag. You're given an approximately 700 megabyte tar file containing a Docker image. The challenge is titled SSHD, which strongly hints that the SSH server is the primary focus. To get started, I generated a file tree of the archive and asked Gemini.
I'm working on a CTF challenge. This is the archive I've been given. The challenge is called SSHD. What should I look at first?
Gemini suggested a few initial steps. Check configuration files, search for SSH keys, and review any logs. The SSH config didn't reveal much, aside from use privilege separation being set to no. However, the apt logs show that SSHD was installed along with Vim, ltrace, and GDB. Gemini also identified CVE 2024, 6387, known as regre-SSH-ion. On further inspection, I found that the SSHD binary is patched, and there's a 2 megabyte crash dump located in the core dump directory. Time to examine what was patched in the binary. Even without symbols, log messages make it easy to pinpoint the modified functions. The first patch disables sandboxing, while the second attempts to prevent crash dumps, yet we still have one. Let's dive into that dump now. When loaded into GDB, it complained about missing modules, but at least we could see the register values. Notably, RIP was set to 0, and the call stack showed that the last function called was from liblzma. So, I loaded liblzma into IDA. The cause of the crash became immediately clear. There was a call to delsim, followed directly by a function call without checking the result. Since the result was null, this caused the crash. Interestingly, the requested function was RSA public decrypt. This not only gave us all the parameters, but also hinted at something deeper. I had already named this function hook, because if you look up its cross-references, you'll find it's called from another function that logs a very specific string. Googling that string leads you to the PLT hook library. At this point, you might be asking, why is RSA public decrypt being called from within liblzma? I had the same question. A quick search for liblzma RSA public decrypt reveals an intriguing story about an open source developer who inserted a backdoor into the package. The method used? A hook on RSA public decrypt within liblzma, exactly what we're seeing here. Back to the challenge. Since we had all the parameters in the dump, I figured the next step was to properly invoke RSA public decrypt. I asked Cursor to generate the code, plugged in the parameters, and it executed without errors. However, the decrypted output wasn't particularly useful. Looking again at our hook function, there's a comparison against a magic value in the input data. If it matches, the code allocates memory and executes content from there. We also noticed the string passed to Dulcim was deliberately incorrect, explaining why RIP was 0. The magic value did match the data in the dump. Before executing the shell code, it's decrypted using data present in the input stream, also in the dump, and it's re-encrypted afterward by the same function. Feeding both decryption routines into an LLM, it identified them as cha-cha or salsa. This was also hinted at by a string literal. Searching led me to a GitHub repo with a .hpp implementation of cha-cha. I asked Cursor to write decryption code using this header and the same input I used for RSA testing. It didn't work, the output was garbage. So I copied IDA's pseudocode decompilation of the cha-cha function, recompiled it with the correct parameters, and now it worked. Turns out, the GitHub repo by user 983 had a buggy implementation. I switched to a better one by Marciju. With the shellcode decrypted, I analyzed it in IDA and saw it made numerous syscalls. I connected IDA to Cursor using Mr. Exodia's MCP server, which allowed Cursor to annotate, rename functions, and summarize the code. It worked well overall, though it struggled with stack variable names.
The shellcode acts as a client connecting to server 10.0215, port 1337. It receives a 32-byte key, a 12-byte nonce, and a file name. It reads the specified file, encrypts it using salsa or cha-cha, and sends the resulting ciphertext back to the server.
I was initially stuck, thinking the transferred data was lost. But since the crash happened right after shellcode execution, I realized we might still have the function's stack frame in memory by scanning downward from the stack pointer. And we did. The file name was still there. The next step is to have Cursor write a Python script using the Unicorn emulator. We'll map the shellcode, initialize the stack with the data from the dump, and run it from the encryption routine. Given how cha-cha works, re-encryption with the same parameters should yield the original plaintext. And yeah, finally, there is the flag. Note that I had to manually set encrypted file size variable because it was overwritten in the dump. The size was obvious when you look at encrypted data. Alright folks, that's it for today. The last challenge took me a while, so if you found it interesting, drop a comment. Should I continue?